Welcome, everybody, to today's JMP Academic Live webinar, Building, Diagnosing, and Interpreting Linear Regression Models. I'm Ross Matusalem, an academic ambassador with JMP, and I'm going to be delivering the webinar today. Thank you all for taking a little time to learn something about JMP. Thought I would just pop my camera on for a second to say hello to everyone before turning it back off here just to save up a little bandwidth. So good to see you all, at least virtually, in the participant list, and I see a lot of familiar faces. So welcome back to those of you who've been joining us for previous webinars. Before we get going here, just a couple routine announcements. First off, this webinar series is one of the many ways that we try to support university teachers and researchers here on the JMP academic team. So just know that in addition to these webinars, you have access to a lot of additional support from our team, including free one-on-one support calls just to help you figure out how to use JMP more effectively, whether that be in your research or in your teaching. We also offer group workshops for you and your colleagues, or maybe you and your lab assistants. We can also do classroom presentations, really anything to help you and other people you know who use JMP just get more out of it. We also offer a suite of free teaching materials. These include things like case studies, sample data sets, quick video tutorials on how to perform specific actions in JMP, and a whole lot more. We make these materials available just to help maybe lighten your teaching load a little bit or complement your course and what you already are doing in it. So if you are interested in checking out our free teaching material library, head on over to jmp.com/teach. So we're about to dive into our topic for today. Please feel free to ask questions throughout, and I'll do my best to answer them. I'll try to pause occasionally to pick up some questions and then also save a few minutes at the end. For your questions, please do use the Q&A window. It is the window in your Zoom interface that looks like two overlapping speech bubbles. Using that as opposed to the chat just helps me keep track of which questions have been asked and answered. It's a little easier on my end. So please go ahead and identify that Q&A tool and pop it open, and then type your questions in there anytime that they pop into your mind. So with that, we are going to get started building, diagnosing, and interpreting linear regression models. So we're over in JMP now. And today we're going to be working, we're going to see a number of data sets, but we're going to work mainly with this fitness data set, which is in JMP's sample data library. In fact, all of the data sets we're going to work with today can be found in JMP sample data library by going to help and sample data. So this data set is on 31 individuals who ran 1.5 miles as part of a fitness test. Our critical dependent measure is their oxygen uptake, measured on average throughout their run. We also have the time that it took them to run 1.5 miles. We have their age, weight, and also their sex, male or female. So we're going to work mainly with these data today, and we're going to build a regression model that models oxygen uptake as a function of these other variables. Now, looking at the background poll that I see most of us have responded to, looks like there's a pretty wide range of expertise in linear regression, ranging from a handful of folks for whom this might be new, through a bulk of novice and intermediate regression users, and then a couple experts. So I do want to just start out at the very beginning, level setting with what our linear regression model is. And hopefully for all of us, even those who have really no regression expertise, this will be intuitive enough to kind of understand what we're doing when we create a regression model and why we might want to do that. So I think most of us, even if we've just encountered regression models, say in popular media, are generally familiar with the idea, and it looks something like this. Here I have a scatter plot where age of the runner is on the x-axis and oxygen uptake is on the y. And I have a line fit to these data that captures the trend. So we can see the older that the runner gets, generally the lower oxygen uptake that we observed. So this that we're looking at, this is a simple linear regression. We have one x variable or one factor, age. We have one y variable or response, that's oxygen uptake. And we have this line capturing the trend. And that line is defined by this simple equation here, where oxygen equals 62.42 minus 0.3156 times age. And this is, at its heart, what a regression model is. We model the mean of y, so that is mean oxygen uptake represented by the blue line, as a function of one or more x variables. And that model takes the form of a linear equation, where you might say y bar, which just is the mean of y, equals some intercept, here about 62, plus some parameter, beta 1, times the predictor value, or the factor value, in this case, age. Then we might include additional factors as well. And so we'd have beta 2 times x2, all the way up to beta n times xn for however many effects that we have in our model. And we can construct models that include one effect, whether that be continuous or maybe even categorical, like sex here. So normally we think of comparing two groups as a t-test situation, which you can use a t-test there. You can also do the same analysis in a regression context, and we're kind of seeing a visual depiction of that here. So you can use both continuous and categorical factors, and you can include one or multiple factors in a model. We're going to deal mostly with a situation with multiple factors in a model, what we would call multiple regression today. Now, these are useful, these models, for both explanation and for prediction. So that is determining maybe which factors matter and how, what size and direction their effect are. And then also actually maybe predicting y given some x's. So for example, if we have age here, we can infer that the relationship between age and oxygen uptake is negative. So that might make sense to us. We can explain something that way. We might also want to predict oxygen uptake as a function of age, and we could even use this line. I mean, here I'm just going to basically just trace on the line to find out that, for example, an individual who's 45 years old, we would expect an oxygen uptake of 48.3 on average. So we're going to see how to interpret models and use them for explanation, also tools for using them for prediction today. I do want to highlight as we go here, we are going to be using least squares regression today. So this is the standard or vanilla approach to regression. It's the one that we probably all learned in our very first statistics course. Now we're going to be using a tool that's general purpose in JMP. It's called fit model, that allows us to fit regression models using a variety of different techniques. So while we're going to be doing least squares today, we can also fit, for example, mixed models. We can fit generalized linear models, so models with non-normal response distributions. We can do logistic regression, which is a form of generalized linear model. We might use variable selection techniques like stepwise regression. So regression is a really big area. We're just going to be focusing, like I said, on just kind of standard least squares regression today. And so we're going to break it into three parts. We're going to first look at basically how to build a model. Then we're going to look at model diagnostics. So that is trying to figure out whether our model is good or if it might exhibit some kind of problems that require us to address them. And then after that, we are going to take a look at how to interpret models. So just our model overall, say how well does our model fit the data, and then also interpreting the individual effects that we put into our models. So let's get started. So first off, let's talk about building models. Now, we saw before in that graph, I closed it a little prematurely, a simple model here of oxygen uptake by age. So let's start with just simple regression and how we would build that model, or put another way, how would we specify the model effects? So that is what goes all on this side of our regression equation. So let's begin with just this simple regression example of oxygen uptake by age. When we're looking at just situations with one X and one Y in JMP, the tool of choice is often a tool called fit Y by X that you're going to find under the Analyze menu. So it's the second option right below the distribution platform here. So to fit that regression that we just saw in the graph, I would go to fit Y by X, put age as my X factor variable and oxygen as my Y response variable, and click OK. Now, in this particular tool, fit Y by X, we're typically presented with just a graph or a really basic output, and then asked to perform or select which analyses we want performed by that tool. And so we're going to go to this red triangle menu. And for those of you brand new to JMP, and I know there are at least a few of us here, you'll see these red triangles all over JMP. They're where the majority of JMP's capabilities live. We'll go to this red triangle and we'll choose fit line. And so you can see we get our regression equation right here. So that matches the one that we saw on the graph with an intercept of about 62 and then that negative 0.32 slope. And we get a number of statistical outputs down below, which we're going to ignore for now. We're going to spend a lot more time with those when we talk about model diagnostics and model interpretation. But this is just to show you the easy way to do a very simple regression using this fit y by x tool. Now, if you want to work with your linear regression model a little more using fit y by x, you will notice next to where it says linear fit, you will have this red triangle right here that allows you to pull up other options. For example, putting confidence curves, say, on the fit like we had in that graph, or maybe we'll talk about residuals a fair bit going on, but I think some of us probably know what those are. If you want to save your residuals, for example, you would find that option there as well. Now you can do simple regression in another tool as well, that fit model tool that I mentioned. We're going to spend the rest of the time in that tool starting right now. I did just want to point out this fit y by x example for those of you who have a good use for just a kind of quick and easy simple regression tool. So let's construct a multiple regression. So one where we have multiple x's using this fit model tool. So just to preview kind of where we're going here. Here I have a model that includes, in this case, the main effects of our 4 variables. So the runtime, age, sex, and weight. Here's a representation of the equation defining that model. So an intercept of 86, an effect of sex on the order of about 1.4 difference between males and females. Here are the slopes for age, weight, and runtime. And then if you're not familiar with JMP, you are now seeing one of the most powerful tools, in my opinion, across all of JMP, the prediction profiler. This is a tool right here that allows you to interactively explore your model effects and what predictions your model makes. So you have one pane for each of the 4 factors entered into the model, and you can see their values in red. And then on the y-axis, you can see the predicted oxygen uptake with the predicted mean in red, and then the confidence interval around that predicted mean in blue. And so I can switch between males and females interactively, or change the age, weight, or runtime variables to see how that actually affects the predicted oxygen uptake. So how would I go about actually building this multiple regression model using fit model? And so this is going to get into really just how to use this fit model tool to set up the model that you want to build. So let's close this down and go to Analyze and Fit Model. So we have a few different fields right in the middle here where we can place our different variables, which we can find on the left right here. So first thing, we want to specify our y, or our response variable. So I'll select oxygen and place it into the y role. And now I construct my model effects. So everything on that right side of the regression equation down here using a simple list structure. And here's how we do that. You'll see these 4 buttons to the left of that big blank box. The add button is how we create main effects. So let's say that I wanted to just do that simple regression we did before. I could grab age and click add, and now I have a simple regression model where oxygen uptake is a function of age. Let's keep our dialog open and then actually run that model to see what we get. So here we go. We have this age by oxygen plot that we had seen multiple times before. We get our parameter estimates, which are those values from the regression equation right down here, which we can see match what we saw already. So we've done essentially what we saw in the graph at the outset, what we did with fit y by x, but now we're just in a more general purpose tool, which allows us to build multiple regression models. So let's do that. Let's add sex, weight, and runtime as well. And so now when I click run, we are at that model that I just showed you with those 4 main effects in them. And if I wanted to pull up that regression equation that we saw, I can go to the red triangle and under estimates, choose show prediction expression. And if I want to pull up the prediction profiler, I can go to factor profiling and profiler, which now places our profiler down at the bottom as we had before. Okay, so that's pretty simple. Now, for those of us who might not be entirely familiar with linear regression, and perhaps one of the terms that I've tossed around a couple times now, main effect, there's a particular point that I would like to make right here. So in a model where we have just what we call the main effects, that is the effect of age, the effect of sex, of weight, of runtime. When those are the only effects in our model, what we're saying is that each one operates independently of another. So let me make this profiler a little bigger. And so let's consider the effect of sex, which we said was on the order of about 1.4. So it's actually just double this value, which we'll get into in a little bit. So you'll notice as I change from female to male, the oxygen uptake predicted drops by approximately 1.4, as we would expect. Now notice when I change, say, age, that difference between males and females, relatively, it stays exactly the same. So that's saying that as people get older, they generally have lower oxygen uptake, and it doesn't matter whether you're male or female, that lower oxygen uptake is about the same. And this is a characteristic of what we call a main effects model. Each effect is independent of another, which might not necessarily reflect reality. For example, it could be the case that the effect of age is, relatively steep for males, but relatively shallow for females. And if that were the case, we would want to include that possibility in our model. And so we need to include what we would call interaction terms in the model to account for that. So let's close that down and include some interaction terms using this cross button. In fact, what we'll do is select sex and age and click cross. And now you can see we have what we call an interaction term in the model. And if I run that model and pull up our profiler, you'll see what our model is able to capture now. So without making it, actually, no, let's make it a little bigger. It looks a little small on my screen here. So now, as I change from female to male, if you look to the left at that effect of age, you can see that for females, it's negative, and for males, it's relatively flat. Now, whether that's actually true or not, whether we're actually capturing reality or whether we might be modeling random noise is a separate question. In fact, it looks like maybe we have a statistically significant interaction if we look back up here. But the point is that including these interaction terms in our models, what allows the model to capture the potential for the effect of one variable to change as a function of another. And so we might want to use the cross option to include potential interactions in our model that might be relevant. Now, we actually also, as it says, we can include quadratic or cubic terms in the model as well. So those are terms that allow our model to exhibit some kind of curvature. For example, let's say that I wanted to have a term for curvature in weight so that it doesn't have to be represented by a straight line. Well, I could cross weight with itself, giving us weight squared. And if I run that and we look at the profiler here, you will see down at the bottom that the effective weight now exhibits some curvature. Now, if we look back up here, we might say, well, it doesn't look like I have statistical evidence that that curvature is real, that in reality, that curved line is true, but our model can at least try to account for it right now. So we use this cross button to introduce interactions and higher order terms like quadratic, cubic terms, and so forth. And that's also just a little bit on what those terms are and what they actually do to our regression model for those of us who may not be familiar. Now, building out large complex models might get a little cumbersome if you're just constantly manually adding effects and crossing effects with others. So we have these macros, which allow us to take shortcuts to common model structures. Just to show you one example, if I go to the macros and go to factorial to degree, let's see what happens. Oh, first I need to select all of my predictors, and then we'll do that. So what just happened? Well, I have my 4 main effects, and I also have every possible 2-factor interaction built into the model. In fact, that was because we went to factorial to degree, where degree was set to 2. Had we set degree to 3, we would have gotten everything up to the 3-way interactions. So this is just a quick way to be able to specify a specific model structure without having to manually add and cross everything myself. A couple other things to note about this model building window. up in the top right, you see two drop-down menus, personality and emphasis. Personality, as we kind of saw before, is where we select different regression tools. For example, when I have a lot of potential terms in a model, I might want to use a procedure to select those that belong in the model and exclude those that don't. So I might use stepwise regression, or I might go to generalized regression, which includes penalized regression techniques like the lasso or elastic net. The emphasis, on the other hand, doesn't change the statistical technique we're using. It actually changes the amount of information that is initially provided to us in the report. So let's run a minimal report emphasis, and you can see we get a report that has a few sections by default, which we'll get into a little more in a moment, but you can see we just have these 6 report sections provided automatically. Now, if I went to, let's say, affect leverage, I'm going to get the same model, but by default, a report with more information in it. For example, these leverage plots, which we're going to take a look at in just a moment as well. Now, whether I use minimal report or affect leverage or affect screening, the other option, you always have access to whatever outputs you want, again, under these red triangles that we've been seeing everywhere. So you'll notice there are a lot of different things that you can pull up depending on exactly what you want to look at. Me personally, I often go with minimal report just to get the most quote unquote bare bones report and then build it out as I go. So I'm going to pause for just a moment and take a look at the Q&A to see what questions have come in so far. So I see one question, what do the colored numbers at the left of the prediction profiler represent? So if we pull up a model, let's go back to our minimal report and pull up that prediction profiler. So I believe we're probably referring to these numbers right here. So the red number is the predicted mean of our Y variable, in this case, oxygen uptake, at these specific values that we see here of our X variables. The blue numbers are a confidence interval around that value. So we would say that we would predict on average a female of age 47 2/3 and so forth would have a mean oxygen uptake of just under 46. But the confidence interval around that prediction is from 44 to 47.9 approximately. I see another one. Why does crossing weight or some other variable with itself show a quadratic? So that refers to, let's say, oh, we don't have it down here. Just simplify. Let's grab weight and cross it with itself. So this is, when we do this, we're basically telling JMP that the model should include a term that is weight squared, weight times weight. And anything squared is itself a quadratic, and quadratic functions have a certain shape to them, like the one that we saw. And so this is just allowing for the model to, if it deems fit, include a quadratic curvature effect for weight specifically. And we have another question, one more. Don't the interactions cause multicollinearity? We are going to get to multicollinearity in a moment, but the answer is that depending on how you actually enter them into the model, you can induce multicollinearity. For those who don't know the term, multicollinearity just means correlation among the different effects in your model, which is generally a bad thing. JMP by default actually centers all effects involved in higher order terms to help avoid this problem. So for the person who answered that, hopefully that one makes sense to you. If not, we're going to talk about it a little bit more shortly here. All right, so we've taken a look at how to build models. Next up, let's talk about model diagnostics. So that is how to identify common problems with models. And I'm also going to provide you tips on remediation. So that is on how to fix these problems if you come across them. Because of the amount of time we have here, just these hour-long webinars, I'm not going to demonstrate the remedial measures, but I hope that just learning about diagnostics is still useful to you, kind of like it's useful to be able to read the dashboard on your car when you're driving. If you see, the tire pressure light come on or the brake light, or you see the engine temperature getting too high, you might not know everything about what causes that or how to fix it, but at least it's enough to tell you that there's a problem and that you might want to go talk to an expert, say a mechanic. Model diagnostics and regression can be the same way. Just knowing what to look for that might signal a problem is really empowering, and that it tells you if you can move forward using your model to explain or predict things, or whether you might want to step back and either fix the problem yourself if you know how, or seek the advice of somebody who can help you out. So let's talk about a number of different model diagnostics through these 6 common problems that I have listed here. We do want to save time for model interpretation, so we'll get through as many of these 6 as we can. Let's first talk about one that, in my experience, actually is left somewhat implicit when we first learn about linear regression, and that is the need for linearity and the potential to violate it. So when we talk about linearity and the potential to violate it, what we mean to say is that linear models really are only appropriate for capturing linear relationships. So when we first looked in our fitness data in Graph Builder here, we saw that a line of this nature seemed to be a reasonable approximation of the true relationship between oxygen uptake and age, or maybe oxygen uptake and weight, and runtime, and so forth. But it's not always the case that a straight line, or as we saw with the quadratics, even a line that exhibits some curvature is in fact an appropriate approximation of the truth. So let's actually take a look at an example here. So here are just a few different functions that I cooked up in JMP to drive the point home. So let's go to Graph Builder now and actually graph these. So if I put X on the y-axis, let's take a look at this first relationship, which is actually exponential growth here. And so the blue line that we see fit to these data is actually, it's a flexible fitting method called a spline, and it seems to capture this relationship pretty well. Now, if I select the linear regression element up here, you can see that just a straight linear regression line is a very poor model to capture this exponential relationship. Now, under degree, I might even put a quadratic term in, and that allows the line to exhibit some quadratic curvature, but we can see it's still not a great fit. For example, it starts to swoop back up in the tail here, and that doesn't appear to capture reality. Maybe we'll get a little closer with a cubic, but honestly, I don't know how much better, because I don't know that it really falls off like this at the end either. We could encounter something like, let's say, a step function. So it looks like the true function actually exhibits some kind of step pattern or sigmoid shape like this, and even a model with cubic curvature, and it doesn't seem to capture it well. Or maybe we would have an even more complex function, which seems to rise to some kind of peak before dropping, leveling off, dropping again to a trough, and then rising. And again, using some kind of linear equation, for example, we could actually pull up what the equation is governing the line that we've tried to fit, is just not a good approximation of the true relationship. So we generally want to make sure that our relationships that we're trying to capture actually are appropriate to be captured with a linear model, which, as I've been driving home now, they can exhibit curvature. So when we say linear, we don't necessarily mean straight. We actually mean an equation of a particular form, but it can only capture curvature of certain types. So if you can't capture it with one of these equations, it's probably best to do some other type of model here. Now, let's actually talk about how to diagnose whether you might have relationship that's not appropriate for linear modeling. We already saw one way is basically just graph them, and you might be able to tell right off the bat. Let's take a look here at the Boston housing data set. So here we have median home value across 506 different districts in the city of Boston, and a bunch of factors we could use to actually predict median home value. For example, the proportion of individuals below a certain socioeconomic benchmark. We might have the average age of the home, or average number of bedrooms, and so forth. So this is actually a pretty common data set that you'll see in a lot of discussion of regression and predictive modeling. And let's say that we built a regression model. Now, here I'm in Fit Model, and I built a simple regression of that socioeconomic status variable as our factor and the median home value as our response. And we can see, actually, as we did before with those graphs, that this doesn't look like it's capturing the relationship very well. It actually has some kind of exponentially decreasing function, it looks like. Now, what happens, though, if we do multiple regression? So here I've included all of our predictors as main effects. I believe there are 11 of them in all. There's no great way to just look whether an 11-dimensional plane fits our data particularly well. So we need some other way of assessing that relationship besides just graphing the data. And so one thing we can look at is a plot called the actual by predicted plot in JMP. So if I go to the red triangle and go to row diagnostics, it lives right at the top here. And so what we have graphed is on the x-axis, the predicted median home value from our regression model. And then on the y-axis is the median home value that we actually observed. And so what we typically want to see in these plots is just random scatter around the line, suggesting that our model is basically fit straight through a cloud of points that don't exhibit any peculiarities to them that might suggest nonlinearity. And you might look at this one at first glance and say, oh, well, that doesn't look too bad. But if you look closely, it actually looks like maybe it has kind of this slight swooping shape to it, especially as we start getting into the higher median home values. And so while this could be caused by other things, say a term, either a factor or an effect among existing factors that isn't included in your model and should be, another possible conclusion here is that you might have nonlinear relationships to account for. And so I might actually go back, for the sake of time, I won't now, but go back and start graphing the individual relationships. In fact, we even saw one that LStat by M value, and it looked like that was probably nonlinear, and that might be part of what's going on here. So just to contrast, let's actually bring our fitness model back up. So here's one that we're going to work with in a little bit. And we can check whether we believe we violated linearity at all here. So I'm going to go to row diagnostics and plot the actual by predicted. And here, in contrast to what we saw with the Boston housing, it looks pretty good. I mean, we just have kind of random scatter showing no clear patterns or trends. And that's what we would like to see. So now the next question is, well, if I find myself, sorry, trying to get rid of that. If I find myself in a situation with this nonlinearity, what do I do? Well, one option is to transform your y variable to try to linearize the relationship. You might use some kind of exponential transform or log transform. But really, there are a lot of other modeling techniques that are available to you that can capture these relationships without the need for a transform. For example, nonlinear regression, flexible fitting methods like splines or Gaussian process models, or we might call machine learning techniques like decision trees or neural networks, which can capture highly complex relationships. So that's the first thing we want to do when we're building a model. Let's make sure that a linear model is the one that's appropriate. What we want to do next is assess the assumption of normality and whether we're violating it. And for any of us who've taken an intro stat course, we've probably come across this. We may have heard it even mentioned, you know, your data have to be normal or something like that to use linear regression, at least this least squares regression that we're talking about here. And when we say this, what we are really saying is that underlyingly, least squares regression assumes a normal distribution of the residuals. Actually, more generally in regression, what we're saying is that it assumes a normal distribution of the response y conditional on our all the effects in our model x. So it's basically building a model where we take all of our x's, plug them into an equation, it spits out a mean of a normal distribution. And then we assume that what we'll observe is drawn from that normal distribution. So we can assess this in a number of different ways. One of the ways, and I'll just kind of highlight it now, and we'll go back with our fitness data here, is to actually just look at the residuals. So I don't know that I've defined them explicitly yet, but the residuals are just the difference between our predicted values and our actual values. So really, it's the difference between the points here and the red line. So if we go to the red triangle, we can go to save columns and save our residuals to our data table. So here they are in this column. And then I could just right click in that histogram and go to open in distribution to see what the distribution looks like, hoping that it's at least approximately normal. And so here it looks normal enough. And it actually is the case that linear regression, when you have a good number of observations, is relatively robust to violations of normality. And so we're starting to get there with 31, though a severe violation might cause problems for us. It might actually cause some problems with our parameter estimates and the accuracy of predictions out of our model. Now, I do want to highlight here that what the assumption is about this distribution of y given x. It's not just the distribution of y itself. So let me get this back out of here and illustrate with a quick example that if you've taken a linear regression course, you may have seen one quite like this. So let's say that here is our y variable data. And if we take a look at the distribution, it is clearly not normal. We actually see that it has these two peaks. We would call it a bimodal distribution. And so we might say, oh, but I thought our data had to be normal for linear regression. I have a problem. Well, that's not necessarily the case. In this example, we have simple two-group design of a study. We have groups A and B. And as you might guess, one of these peaks belongs to group A and one of them belongs to group B, such that if we build a simple model, so we'll put group as our one factor and data as our response. So we're using linear regression to essentially conduct a t-test here. And now we get our residuals out and plot them. You'll notice that those residuals appear to be normal. And that's because what we really have is just two normal distributions whose means are spread apart a tiny bit. We have one distribution for A and one for B. So it's not necessarily the case that just because your raw response variable is non-normal, that your residuals aren't. It's just an important thing to be aware of. Now let's take a look at a different example briefly here. So here I have data. This is the fishing data in the sample data library, where our y variable is the number of fish caught by people in a park. And we can see whether or not they use live bait, the number of poles they were using, so the number of poles or perhaps people, and so forth. So those of you with more regression experience might look at this and say, oh, well, this must be a Poisson regression because this is count data. So if you were there, then that's good. That's actually the situation we have. But a lot of us wouldn't necessarily know that. And we might think that linear regression would be appropriate here. So let's say I built a regression model. I can already see my actual by predicted plot looks a little funky. If I save my residuals and plot them in the distribution platform, they look really positively skewed. That's not a great sign. There's actually an even more direct way to assess whether they're normal, and it's something called the normal quantile plot. You're going to find that under the red triangle, row diagnostics, plot residual by normal quantiles. So I'm just going to expand this and ignore those 2 points for a moment. Without getting into details, what we're looking at in this plot of residuals is a representation of what the residuals should do or should behave like if they follow a normal distribution. That's in red. And then what we actually got, and that's the black points. So if our residuals were normal, they should fall somewhere along this red line, ideally with the variation around that line limited to inside this confidence curve here. And we can see we have a pattern that is really suggesting that they're not normal with this somewhat S shape. Now, if we go back to our fitness example, just to contrast, we could pull up the normal quantile plot, and you can see what a good one looks like, where the points are all well within those curves and hugging that line nice and closely. So here we have clear evidence that we have non-normal residuals in this fishing example. So what would we do about it? Well, we could transform our y variable. A common transform is actually the Box-Cox transform. It's an exponential family transform that can help get your data to behave more normal, so to speak. And if you go down to factor profiling, you can actually find the tool to do a Box-Cox transformation. But here, in this particular case, we actually know a better response distribution. Like I mentioned, that Poisson distribution, which is a distribution of discrete counts going from 0 in integers up into positive values here. And so I might want to use the generalized linear models to assume that distribution. So if I went to fit model, I would actually, under the generalized linear model personality, find the Poisson distribution. Or if I have jump pro, under generalized regression, which includes many response distributions and also penalized regression techniques, I might choose Poisson, or you can see we have a large number of other distributions as well. So that's the assumption of normality. And I think it's one that folks trip often over somewhat often, just with what exactly we're assuming with respect to what is supposed to be normal. So just remember that it's the distribution of y given x, which in the context of least squares is the same thing as saying the distribution of the residuals. All right, so next up, non-constant error variance. So the idea here is that in least squares regression, we assume something that in statistical terms is called homoskedasticity. What that means is that the variance of that distribution of residuals that we've been looking at doesn't change depending on where along the regression line we are. It's always the same. And that's not always the case. So if we look, let's see, first at our fitness example, we can actually see an example of when this holds, and then we can contrast it with one where we violate it. So we're going to take a look at the residual by predicted plot, which is under the red triangle, row diagnostics, residual by predicted. So what we're looking for, if you imagine that these are the residuals along the regression line, which would be in blue here, you're just looking for totally random scatter, which essentially we see here. We don't see any evidence of the variance, the scatter around the line, changing at any point. Let's contrast this with an example from the Hollywood movies data set, where we can construct a model among a number of different movies of its world gross in millions of dollars, according to, say, what genre it is and how many theaters it was shown in an opening weekend and so forth. And so here is a model with some main effects and interactions. And if I pull up the residual by predicted plot, we can see a distinct pattern that contrasts with what we have in our fitness example. So whereas in the fitness example, it looks random, here we have this pattern where it's clearly getting more and more scattered as we predict higher and higher world gross. This is the canonical megaphone pattern that you might run into that suggests non-constant error variance. Now, you might see other patterns besides this canonical megaphone, for example, maybe something that looks something like this. So it's at either end, you see higher variance. The idea is that you just want to see uniform scatter all the way across. And if you don't, and you violated this, again, this is something where linear regression can be reasonably robust to violations of this particular assumption. But once you violate it severely, your estimate of the true error in your model can get thrown off, which then throws off your confidence intervals, throws off your hypothesis tests. So if you encounter a situation like we're seeing with this Hollywood movies data, you're going to want to do something, for example, transform your Y variable to stabilize the variance, or use a different statistical technique, for example, weighted least squares or log linear variance models that can help you account for that change in variance. The log linear variance model actually just models the variance, well, really the log of the variance according to some linear combination of your predictors. So you basically have one equation that governs the mean and another that governs the log of the variance. And this is a personality that you can find in fit model right here. Okay. So let's see how many more of these we can manage to discuss before we move on to interpreting our model. Another assumption of linear regression is independence of observations. So in particular, that the residuals are independent, so that if we know the residual for one observation, it gives us no information regarding the residual of some other observation. In our fitness example here, that's generally going to be the case. We just have 31 completely independent individuals. We have no reason to believe that they are related in any way, but there are some common ways in which we can find non-independence in our data. So one is repeated measures. That is, we measure the same individual or unit multiple times. Here's an example of measuring roaming radius in miles for 2 different species across the 4 seasons of the year. Now, for each individual, we measured them 4 times. So here's in the fox category, species or subject number 1, we measured them each season, subject number 2, each season, and so forth. So we would believe that the observations for, say, subject number 1 would probably be somewhat correlated with each other. Maybe subject number 1 just has, in general, a lower roaming radius than, say, subject number 3. When you have multiple or repeated measures like this, you generally have a violation of non-independence that needs to be accounted for. And you can actually figure this out up front by just knowing the structure of your data. Now, a different version or a different violation can occur when observations are correlated across time. So here we actually have ozone concentration measured monthly starting in 1955 up through the 70s. And we might want to know whether some interventions meant to bring the ozone concentration down actually had an effect or not. But we probably know that ozone concentration can't just month to month vary totally independently. That is to say, if we know something about last month's concentration, it tells us something about this month's. So in this situation, we probably have what we call autocorrelation. In fact, just to show briefly, if I were to take, let's say, the lag of ozone concentration. So now I have the ozone concentration this month, and what it was last month. We can briefly here compute the correlation. And we can see that that correlation is relatively high at about 0.735. So we're likely to violate this notion of non-independence if we were to, let's say, build a model where we modeled ozone concentration as a function of these interventions. Now, looking at this output, we don't necessarily know that we've done that. So what are some ways that we can try to figure that out? Well, first off, we could look at the residual by row plot, which is another option under these row diagnostics. So if our data in the table itself are time ordered, we can actually look for trends in this residual by row plot. And we actually see a slight trend right here instead of random scatter like we're typically looking for in these residual plots. We might also run a statistical test of what we would call first order autocorrelation here. So that is just something being correlated with itself one time period, or in this case, one row previously. And that's living all the way at the bottom of these row diagnostics. So when we do the Durbin-Watson test, if we get a statistically significant result, we have evidence that there is some correlation from row to row in our data that we actually want to account for here. Now, what do we do? Well, we could just model the factor that's giving rise to non-independence. That is, in some cases, we actually just take the lagged variable and include that as a factor in the model. And that's one way to do it. In this example, I might actually use time series methods that might be more appropriate for exactly what I'm trying to do. But in other cases, if you're just carrying out a study over time, but you're not necessarily trying to do time series forecasting or anything like that, this might be an effective way to help deal with that autocorrelation. But perhaps a better way is actually to just use a class of models known as mixed models, which can just model that non-independence directly. So in JMP Pro, there's the mixed model platform. And under, say, repeated structure, you could choose an AR1 model, which is actually just going to model that correlation that we found when we looked at the lagged ozone concentration. You can also use random effects in your model to, say, account for what we saw at the animal example, where you would put subject as a random effect. All right, so we are getting close to time here. I'm going to actually save correlated predictors and outliers for another time. I'm sorry that we didn't have time to get to those. Also recall that at the academic team, we're always available to connect for a little one-on-one chat or a group workshop if you'd like to talk about some of this in more detail. But I do want to make sure that we have enough time to talk about model interpretation just a little bit. So let me close down these examples here and bring our fitness data back. So let's say that we have now fit a model, we've run our diagnostics, we believe that our model is looking pretty good. And now we actually want to interpret this wealth of outcome that, output that has been provided to us. Now, I know when I first started doing regression and looking at some of these outputs, I honestly felt a little overwhelmed. And of course, there's a lot here, but it's a lot of useful information, and getting a basic handle on it actually isn't too bad. So let's give it a shot. So first, let's talk about assessing the overall fit of this model. So that is this model that I have any good or not? So we've actually already looked at one way to assess that, and that is the actual by predicted plot, which we found in our diagnostics menu. Now, when we see this, again, this is just a plot of on the X, what the model predicts, and on the Y, what we actually observed. Those confidence curves, which we see in red there, those actually give us an idea about whether our model accounts for more variability in Y, in oxygen uptake, than we would expect from chance alone. That is, if none of the effects in our model were active at all, or put another way, if all of our model parameters were truly zero. And so when you see separation between that blue line, which represents that model in which all the parameters are actually just zero, if you see a separation between that blue line and the confidence curve, you have some reason to believe that your model must actually be detecting some kind of real effect somewhere in there. You know, we still have to chase down exactly where. This actually is almost a visual depiction of what you're going to see in this analysis of variance table right here, which is a hypothesis test on whether your model accounts for more variance than you would expect from chance. And so if we get a statistically significant result, which we have here, we believe that, yes, that is the case. Now the question is, you know, what might actually be driving our model's ability to account for some of that variance? And before moving on to talk about that, there are a few other things we could take a look at to assess how good our model is. Under the summary of fit, we have a few helpful statistics. For example, R square, which as you can see right here is about 0.87. Now, if you're not familiar with R square, it's just the proportion of variance in Y that is being accounted for by our model. So in this case, it's 0.87. So 80% of the 87% of the variability in oxygen uptake that we observed is being accounted for by the effects that we have entered into our model listed down here. Now, oftentimes people want to try to get a higher R square, that is, build a model that accounts for more and more variance. That's not necessarily a good thing. For example, if you have an R square value of 0.999, meaning that your model accounts for 99.9% of the variance in some response variable, you might start to think that's a little suspect. You might have a model that is what we would call overfit. So that is a model that's actually starting to capture the noise in the data, and it's starting to become distorted in a way that doesn't represent reality, such that it accounts for the data you saw really well, but it's actually going to generalize really poorly. And so R square adjusted is something that can help you in this situation. So R square adjusted is essentially R square, but it's adjusted down for the number of effects that you include in your model. So the more and more effects that you include in your model, if they don't necessarily contribute to the overall R square, is going to cause R square adjusted to go down and down and down. And so it's very good to actually look at this number because by definition, R square itself will just keep going up the more complexity you add to the model, but R square adjusted might not. It might actually fall, and that's a sign that you're starting to overfit your model. Of course, there are all kinds of model validation techniques out there, you know, cross-validation, k-fold validation. There's also model fit statistics like information criteria, all meant to help with this overfitting problem that one might encounter. But the R square adjusted, just living right here, is often a great place to just start. Okay, so in this model, I don't really think we have an overfitting problem. We didn't get through all the diagnostics with it, but this is actually a very well-behaved data set, really good for initial classroom use if you are looking for an example. So I think our model fit is generally pretty good. Let's actually talk about the individual effects in our model. So, you know, what actually is influencing oxygen uptake? Well, we can look at the effect summary, which is a rank ordered list of effects according to p-value or statistical significance. So we can see the most significant effect is runtime with a vanishingly small p-value, followed by the sex by age interaction and so forth. In the effects tests, we actually get hypothesis tests for each of these. So it's basically just fleshed out test statistics behind all of these p-values. In this case, we get the F test for each one of the effects in our model. So you can notice then that the p-values in the effect summary perfectly match those you're seeing in the effect test here. Now, this gets particularly useful when you have categorical factors with 3 or more levels in particular, versus say looking at the parameter estimates, which we're about to now. So just to really, the effect tests are useful when you have any kind of effect that is spread across multiple terms in your model, because it all gets aggregated here. So finally, let's take a look at the parameter estimates themselves. So these are literally the terms from your regression equation. So at the beginning, we saw that I can go to the red triangle and show prediction expression and actually pull the equation up where we get the intercept, so 91.8 plus the adjustments for sex. So we add 0.466 approximately for females and subtract that same amount for males, minus 0.2 times age. And you can see that all of those numbers there actually are just pulled straight out of this table. So we're just looking at it in the form of the regression equation. Now, a few things to note here. One, the categorical effect. Sometimes it gets hard to try to wrap your mind around these. So what we have here, when it says sex female 0.47 approximately, we're interpreting this according to how this was actually entered into the model. That is how it was coded. So this is all about categorical coding schemes when we're doing regression models. So if I go actually to save columns, I can go to this option called save coding table, which is going to be pretty helpful here to help us interpret what's going on. So this coding table is showing us that sex in this model was actually entered either as a value of 1 or a value of -1. So in fact, it was entered as a value of 1 for females and -1 for males, which is something that we typically call effect coding, which means that this intercept represents the mean, and then we adjust up for females and down for males. So it's the difference between males and females, according to our model, is just twice this value. Now, if we wanted to see that directly, there's a nice option called the indicator parameterization estimates. And so if I go to estimates, indicator parameterization estimates, we get those down here, and you can see that sex at 0.93 approximately is actually just twice this value that we're seeing here. So this more directly captures the true effect. And this would be equivalent to entering a value of 0 for males and 1 for females. Okay, now let's actually talk about trying to interpret these. I've kind of implicitly been doing this already, saying that the effect of sex is about 0.93. Here we might say, well, the effect of age, so increasing age by 1 year, decreases oxygen uptake by 0.2. I might actually go to the profiler to try to verify that. In fact, I highly recommend using the profiler when you're trying to understand model effects. So let's say I go to an age of 45, oxygen uptake of 48.27. I would expect it to drop by about 0.2 if I increase by 1 year of age. And it does. Now, I want to pump the brakes though. And with the last thing to leave you with before we wrap up, and this is something that we've probably heard if we've studied linear regression in any detail, is in a situation like we have here, with some interaction effects in addition to our main effects, it's actually the case that it can be pretty difficult to interpret these main effects directly. So here's a simple example. We said that the difference between males and females would be about 0.93, again, double this value. Okay, well, so that means that if we change from female to male, we should see a difference of approximately 0.93. Now you'll actually notice it's slightly off already because I changed age from its mean value. But it's pretty close. But of course, we know that there's a sex by age interaction. So if I change age up, you can actually see that now the difference between males has even flipped. So again, these interactions mean that the effect of one factor changes as a function of another. So this main effect of sex really isn't meaningful. It's not that it's 0.93 for all individuals. It's 0.93 really at the average age and weight and anything else sex interacts with. So it's really important to actually pay attention to these interaction effects. In fact, what we would say here is that the effect of sex actually diminishes that difference or flips from being in favor of females by about 0.35 for every increase in 1 year of age. And that's what we actually see in this profiler as the difference between males and females starts to level out and then even actually show higher oxygen uptake in the males. And so just to drive home the point then, while interpreting some of these parameter estimates, maybe for explanatory purposes, reporting in some of your research papers, if you have statistically significant interactions or just interactions in general that are left in your model, the main effects themselves can't be interpreted directly. They need to be interpreted with respect to the interactions that they're involved in as well. And so that was relatively sweeping overview of building, diagnosing, and interpreting linear regression models, essentially an attempt to do in a 1 hour what you would do in an entire semester. I see a number of questions that have come in the chat. I'm going to hang out and answer all of those for as long as it takes for everyone to have seen everything they want to see. I do just want to highlight for anyone who has to run, of course, you can always email academic@jump.com with any questions that you have. If you want to talk to me or any of my colleagues about this in more detail, or maybe line up a more in-depth seminar or workshop for you, your colleagues, your students, please do feel free to reach out.